So last session, we covered up until CAM, class activation maps. Just a quick recap of what we have been doing so far. We started by visualizing every single layer or every single feature map in different layers by deconvolutional neural networks, by using a deconvolution operation or deconv nets, where you had a combination of convolutions and then unpooling using switches. The next one was very similar. It's also about backpropagating from your output layer to the input layer and then trying to visualize where your neural network is looking at, or in other words, what pixels in your image are responsible for the prediction of your neural network. And we saw that this method using gradients is equivalent to deconvolutional neural networks with a minor catch, the way that you're going to handle your nonlinearity. One of them is going to go look at the output. That's going to be an indicator function on the output. Then you're going backward to the input to your layer. The other one for going backward is going to look at the input to that particular layer. So that's the only difference, the ReLU activation. Then we introduced guided backpropagation for visualizations, which is a combination of backpropagation and deconvnet. And it's going to depend on both your output and input. So you're going to have an indicating function, both on your output and input layers, and then you're going to go backward in your neural network. So all of these are based on derivatives and gradients in particular. This other one, which we covered last session, layer-wise relevance propagation, LRP, has its own backpropagation mechanisms. So it is not based on gradients anymore. It's based on trying to be fair, trying to be conservative. You start with your last layer of your neural network, and then while trying to be fair, you associate relevance to every single neuron from your output going back to the input. And that way you're expanding your function as a summation of the importance of every single pixel in your image. And because it has its own backpropagation procedures, you need to know how do you actually want to backpropagate in a conservative fashion. And that depends on the layer that you have. If your layer is of a convolution or dense type of layers, then this is how you're going to do it. For the other type of layers, we are not going to have time to cover it, but there are also methods for doing that. But you need to devise your own backpropagation mechanisms. Then we moved ahead and learned about LIME, which is about approximating a complex decision boundary locally around one of your data points by a line. You could, in principle, use LIME to set the importance of every single pixel in your image. In principle, you can do that, and there is nothing wrong with it. And then it's going to be similar to the methods that we just covered. Let them be based on gradients or let them be based on your own backpropagation mechanisms. In principle, it is doable, but in practice, it's going to be really computationally expensive if you want to take a look at every single pixel. Because for every single pixel, you need to know, is that pixel, is the presence or absence of that pixel important or not? And then for each one of them, you need to come up with your line. That's why you put together a bunch of your pixels, you call them superpixels, and then you operate on superpixels to be less computationally expensive, and for LIME to be applicable to images as well. Then we moved on to CAM. For CAM, it's a similar situation. You don't want to be working with every single pixel in your image. One cool thing about convolutions is that you're actually grouping together your pixels in the later layers. For instance, a pixel here in one of your layers or in the final layer is going to correspond to a window of your image. And then you are going to have multiple windows. And whatever that you have here is a featurized version of that particular window. And that's why you don't need to backpropagate to the input image. You can stop somewhere around here. Other than that, it's very similar to what we have been doing so far. So they're all under the umbrella of backpropagating something, either your gradients or you're backpropagating something else, like in the case of LRP. And they differ on where you're stopping before you do your visualization. I think it's a good time to switch the gears a little bit and talk about not visualization, but about trying to actually understand what deep neural networks are supposed to do. What do we mean by testing and training errors, and the difference between them? We usually call that generalization error, and try to understand deep neural networks in terms of generalization errors. This was an assignment for you to watch the video online. Do you have any questions about this? In terms of the big picture, we know that neural networks are universal function approximators. It means that they are going to be capable of overfitting. Here is another observation that yes, indeed, they are universal function approximators. And if you have finite samples, it means that you have finitely many data points. Don't look at it in terms of continuous functions. Look at it in terms of samples. You're going to be able to overfit to your samples. You're going to be able, regardless of your data, you're going to be able to find a neural network that's going to overfit. Basically, go through every single data that you have. And here is a proof of that happening. Empirically speaking, neural networks are capable of approximating anything, including noise. Now, here was the question. This seems to be a contradiction. You have some data, training data, you're able to overfit to that training data, but in practice, you see your neural networks generalizing, being able to perform on your test data. So is there something special about the architecture or the way that you are designing your neural networks? This was a large component of what we were doing, where our topic was about large neural networks. Is there something special about the architecture? And the answer is no. Regardless of the architecture, you are able to overfit, even random stuff. And somebody might say, is something special about the regularization process or implicit or explicit regularization processes that we usually use? And the answer is no. Even in the presence of regularization, your neural network is capable of overfitting, even to noise and random stuff. So that's the big picture. There is a comment in the chat. So my interpretation of this was just that it proves all data is capable of being overfit by a neural network. But I'm still confused why regularization isn't necessary. I do understand it might not be sufficient. So you are having a concern about this being necessary or sufficient. I'm not sure how to put it.
I guess kind of my bigger question is, like, it might not totally get rid of overfitting, but it still seems to help a fair amount with things like data augmentation. So why is it that it's not necessary? I get that it's not sufficient to prevent overfitting, but isn't it necessary to get better performance at least?
Oh, so we need to interpret the word necessary here in the context of this sentence, okay? It means it is not necessary to improve the generalization performance. It means that it is actually helping, and you're right in the sense that it's going to help you and your neural network not overfit to some extent, but you cannot say that because of explicit regularization or implicit regularization, I can explain the fact that neural networks have a low generalization error.
Okay, that makes more sense.
At the same time, it is not sufficient. It means that you're going to need more. Something else is actually explaining the low generalization error. Maybe it has something to do with your optimization. Maybe a stochastic gradient descent is doing some magic. And maybe during the optimization process, you actually landing on a local minima rather than a global minima is actually responsible for explaining the good performance of neural networks, despite the fact that they are capable of overfitting. So maybe it has something to do with the optimization process, with a stochastic gradient descent. Okay, any other questions? Okay, perfect. I guess we can move on. This is a very influential paper. And if you want to do theory of deep neural networks, these are actually really good questions to investigate. Why do they generalize? Because in the end of the day, you are not really interested in the performance of your neural network on your training data. You want to take your neural network and put it into production. If that's the final objective, then these are really fundamental questions in terms of asking questions about why neural networks generalize and try to answer them.